Hi, I got a question on what is the difference between the null space of a matrix and the kernel of a linear transformation. By the definitions, there is no difference. The definition of a null space, if I have an n by m matrix, it's a set of vectors belonging to Rm such that the matrix equation AV equals 0 is solved by V. And the definition of kernel of a linear transformation is that it's the set of vectors x belonging to the vector space V such that t of x is equal to the 0 vector. The difference is how you find the null spaces, and in some cases it can be very different, a very different process. The null space of A is found by a procedure. You first are looking for the solution to AV equals 0, and you do this by setting up an augmented matrix and finding the parametric form of the solution set and then expressing that as a span of basis vectors. So this is really procedural, and what's really interesting is if you memorize or are very good at doing this procedural fact and it becomes your definition of null space, then it becomes very difficult to abstract the idea of the null space of a linear transformation. It's very interesting how the mind can work. For kernels of linear transformation, now he uses a different word called kernel. It can be called null space as well, but he switches the terminology to distinguish between the fact that there is no procedure to find the null space of a linear transformation, an arbitrary linear transformation. If it is a linear transformation defined on a finite dimensional space, and you have that means you have a finite amount of basis vectors in the that span the vector space, then you can transform that matrix, that linear transformation to a matrix. We have a procedure for doing that, and then you can find the null space of that matrix and then transform back into the linear transformation. So there is a procedure for finite dimensional linear transformations. So I want to give you an example where there is no procedure, you just have to think about the definition. And for that, I have to go to an infinite dimensional space. I gave you one in class where we looked at the linear transformation that takes functions that are continuous and have a continuous derivative and sends them to the derivative. And in that case, we had to think and use the definition. Here's another example. If I take V to be the set of bounded infinite sequences of the form where you have a component for each component, each component is a real value, and I've written out the form here. So for example, this is a different set, it's a new set, so we have to think about what's in there. 1, 1/2, 1/3, 1/4 is in there because that sequence is bounded by 1, so it's closed off. But 1, 2, 3, 4 forever is not bounded. It converges to infinity, and it definitely goes above any limbo bar that you try to stop and bound it by. So we can think of now sequences that are in this vector space and sequences that are not. This is a vector space that has a 0. The 0 would be the vector with all zeros in the components, and it satisfies all those 10 properties of being a vector space. Now I'm going to define a linear transformation, T of U, to do the following. It takes a sequence and then it shifts that sequence to the left, so it drops off that first component. And this particular linear transformation is called the left shift operator, obviously. This linear transformation is indeed linear, and I'm going to prove that very quickly. I'm not going to go through slowly details, but if I have two arbitrary vectors, u and v, and I have a scalar c coming from R, then I want to show that t of cu plus v is really t of cu plus v separated out, or ct of u plus v. And so I have to add these arbitrary vectors together, scaling in c, and then apply t. Now I've got this nasty vector in white written down here. What does t do to the nasty vector, the infinite sequence? It shifts everything to the left and drops off that first term. So I apply t as a procedure, as an operator to this sequence, and I get the next sequence that I have down at the bottom. Well, I can play with that sequence. I can split this apart into two pieces. I can take all the v stuff and separate it out, and if I'm adding component by component, I get the previous step. And if I look at the first term, I can factor out c, and so I really get that that first term is c times t of u, and that second term is t of v. It's in fact the vector v shifted to the left. And so I've shown the property, the two properties combined as one, that t is linear. So what's the kernel? There's no procedure. There's no augmented matrix. There's no row reduction. I must use the definition. So going to the definition, I'm looking for the set of u that belongs to the vector space so that t of u, it makes t of u 0. Here, as I said before, the 0 vector is the 0 sequence with all components 0. T of u, by definition, shifts everything to the left, so I get u2, u3 with u1 missing. I set that equal to the 0 vector, and I solve component by component. No augmented matrix. I have to solve each component separately. And what I get from this is that all the components must be 0, except u1. u1 was not specified by any of those equations. So just like we have a free variable for finite dimensional spaces, u1 is a free variable here in the infinite dimensional space. And of course u1 can be any real number. So if I can do the same business I do for finite dimensional matrices, I can factor out that u1, and that's the parametric form. So I really have that the null space turns out to be the span of the vector 1, 0, 0, 0, 0 repeating forever. So that's the kernel. It's the span of this vector.